Okay, this is quiz 2. The first question reads, let y equals f of x be the function defined on the interval from 0 to 4, whose graph is shown below. Evaluate the following limits. Write dne if the limit does not exist. Part A says that the limit as x approaches 1 of the function and asks us to evaluate that. Now, if we look at as x gets close to 1, so remember we're moving in the x direction, here is 1. As we get close to that, from the negative side, we're getting closer and closer to 0. From the positive side, however, we're getting closer and closer to y equals 1. Thus, the limit does not exist because the left and right-hand side limits do not match up. So this limit, part A, does not exist. Part B asks for the limit as x approaches 2. Now, if we do the same thing as we move from the negative side, the function gets closer and closer to y equals 2. As we move from the positive side, we're also getting closer and closer to y equals 2. In fact, we're staying at y equals 2. Thus, this limit does exist, and the limit is 2. As the third part C, says the limit as x approaches 3. Now, if we move again from the negative side towards x equals 3, we stay along this y equals 2 line. And if we move along the function from the positive side, we get closer and closer to y equals 2. Thus, again, this limit does exist, and it is 2. Finally, the limit as x approaches 3.5. Now, 3.5 is between 3 and 4, and if we just pick a place for it to be, you can see that it's actually going to be at 1. This line is straight, and it goes from the point 3, 2 to 4, 0, so it has to go through the point 3.5, 1. And again, this is just one straight line. We know now that it's continuous. So in fact, this limit does exist, and it is 1. Okay. The second problem asks us to compute the following limits, and again, write dne if the limit does not exist. Okay, this first one is fairly easy. We can see if we plug in 0, there are no problems here. So we're able to just go ahead and plug it in, and we get 5 over 3. Part B is the limit as t approaches -1 of t plus 1 over t squared minus 1. This one's a little trickier. We can't just plug it in, because if we plug in t equals -1, we get on the bottom -1 squared, which is 1 minus 1, so on the bottom we'd get 0. We can't do that, that's undefined, so we need to do some algebraic manipulation. So I'm going to rewrite this as the limit as t approaches -1 of t plus 1, and then I'm going to factor the bottom into t plus 1 times t minus 1. Now I can cancel that t plus 1 on the top and bottom. Notice I'm allowed to do this. I'm not dividing by 0 because t is only getting close to -1. So we're never actually evaluating at t equals -1, so this is not dividing by 0. So then this is the limit as t approaches -1 of 1 over t minus 1. When we plug in -1, we get 1 over -2, which is -1/2. Okay, part C is the limit as x approaches 1 of 1 over x minus 1 over x squared minus x. Now again, we have the same problem. If we plug in 1, we're going to get on the bottom 1 squared minus 1, which is just 0. So we need to do some algebraic manipulation. I rewrite it, the limit as x approaches 1. Now on the top, I'm going to get a common denominator. So this is the fraction 1 over x minus the fraction 1 over 1. So my common denominator is x, and this is 1 over x minus x over x, all over, and I'm going to go ahead and factor this right now, x times x minus 1. Okay, now if I do some more simplification, I get this is the limit as x approaches 1 of 1 minus x over x, and now this is just a fraction, it's x times x minus 1 over 1, so I can invert and multiply. Now the trick here is to see that 1 minus x and x minus 1 are just are negatives of each other. So I can cross these ones out, and put in a negative 1 here. So this is the limit as x approaches 1 of negative 1 over x squared. Now I can go ahead and plug in 1, and I get that this is negative 1. Okay, part D, the limit as h goes to 0 of 16 times t naught plus h squared minus 16 t naught squared, all over h. Okay, again, can't plug in h equals 0 because I have an h on the bottom, and that would be undefined. So I need to do some manipulation. I'm going to go ahead and begin by factoring out a 16. So notice there's 16 times both terms on top, so I'm just going to factor it out. And I get that this is 16 times the limit as h goes to 0. I'm going to go ahead and square this t0 plus h, and that is t0 squared plus 2t0h plus h squared, minus, there's still a t0 squared, t naught squared on top, all over h. Now this simplifies. I get 16 times the limit as h goes to 0. These t0s, t naught squareds cancel, and I get on the top 2t naught h plus h squared. Now notice those both have an h in common, so I'm going to pull that out. So this on top is h times 2t naught plus h, all over h. Now I can cancel those h's, and this is 16 times the limit as h goes to 0 of 2t naught plus h. Now the limit as h goes to 0 of 2t naught plus h, that's just 2t naught. So I have 16 times 2t naught, or 32t naught. Okay, the third problem says, determine if the following assertion is true or false, and explain its connection to a statement about limits. The statement is, for any number epsilon bigger than 0, there exists a number delta bigger than 0, such that for any number x, if the distance between x and 3 is less than delta, then the distance between 2x and 5 is less than epsilon. Now, the way that I would read this is that I would say that as x gets close to 3, as this distance gets small, as x gets close to 3, then 2x gets close to 5. This distance gets small. Now, when I read it like that, it becomes really obvious. I know that as x gets close to 3, 2x gets close to 6, not 5. So I know right away that is false. Now, the explain its connection to a statement about limits, that's asking you, what do you recognize here? Well, one thing I recognize right off the bat is that this is almost exactly this is the definition of, the precise definition of a limit. So if this were true, it would tell us that the limit as x approaches 3 of 2x is equal to 5, but that's not true, okay? So if this were true, that would tell us that. But that's not true. And in fact, we could actually change the last line so it is true, and then this statement will be the correct statement, that the limit as x approaches 3 of 2x minus 5, or excuse me, of 2x is equal to 6. So what we need to change is we just need to change this number 5 to a 6. When we do that, this correctly tells us that the limit as x approaches 3 of the function 2x is equal to 6.